Hello, Year 12. Today we will be looking at wave-particle duality and the de Broglie wavelength. So just to recap on where we're at so far in quantum physics. Now in 1905, as we may recall, Einstein conducted the photoelectric effect experiment, and up until that point light was thought of as a wave. It behaved as if it was a wave, but then when the photoelectric effect experiment was conducted, it seemed to behave like a particle. So in the photoelectric effect, if you shine a light at metal, it will knock out electrons from the metal if that light has sufficient energy. But if you try to explain this using the wave model, you get the wrong result. It was only by resorting to a description of light as if it could only deliver energy in discrete packets that Einstein was able to describe how this photoelectric effect worked and predict the results that they actually measured in the lab. So Einstein said that light was only giving energy in certain amounts equal to hf, where h of course is the Planck constant and f is the frequency. It either gave all of this energy to the electron or it gave none. So it was all or nothing. It was never half and a half. Now, the confusion was that we considered light a wave, because if you shine light through a double slit, as in Young's double slit experiment, if it were a particle, you would expect particles to go through either through the top hole and give you a bright spot on the opposite side of the screen, or through the bottom hole and give you a bright spot on the opposite side of the screen there. But what we actually measure when you do the double slit experiment is, with light of course, is that it diffracts from both holes, overlaps, and gives you a diffraction pattern on the screen with constructive and destructive pattern that would only emerge if the light beam were passing through both slits and then overlapping the way waves would out of two holes. So this experiment showed that light behaved like a wave, but the photoelectric effect showed that light behaved more like a particle. So light can have wave-like properties or particle-like properties depending on the experiment that's being conducted. So the photoelectric effect can be explained using the idea that light and all electromagnetic radiation behave like particles. However, to explain phenomena like diffraction, interference, and polarization of light, we must use the wave model. This dual nature of light is what we call wave-particle duality of light. Okay. Now, reflection, the phenomena of reflection, is an example where both models actually work well. Now, so light interacts with matter, for example, electrons as a particle, the photon, and we have evidence for this using the photoelectric effect. Light travels through space as a wave, and we have evidence provided by diffraction and interference of light using Young's double slit model experiment. And we also have polarization of light as well. So by 1924, a very, very young, talented, gifted physicist named Louis de Broglie asked the question, is it possible for particles like electrons to also have a dual nature? He said that if light, which we thought was a wave, behaves like a particle, then maybe particles, such as electrons, can also have or behave like waves. De Broglie imagined electrons would travel through space as a wave. If electrons can be shown to be diffracted and cause an interference pattern, the particle must have a wavelength. De Broglie came up with an equation for the wavelength of a particle, which he called the matter wavelength, and is now also called the de Broglie wavelength. So we know already from the wave equation that F is equal to c over lambda, c being the speed of light. We also know that E is equal to hf, or h is the Planck's constant. There's a very famous equation, E is equal to mc squared, but we know that E is also equal to hf. So mc squared is equal to hf, but we can replace f by c over lambda, and we get hc over lambda. Now, one of the c's cancels out, so we're left with mc is equal to h over lambda. So for a particle of velocity v, c is equal to v. Now, this v is very close to the speed of light. We get mv is equal to h over lambda. Okay, that's a very important de Broglie equation there. Okay, we can rearrange that, and we get the de Broglie wavelength is equal to h over mv. So de Broglie was saying that everything in the universe can behave like a particle or a wave, depending on the experiment that's being conducted. So de Broglie set out to find what this wavelength would be. Okay, so he said that the wavelength is actually related to the momentum by the equation lambda is equal to h over p, where p is the momentum and h is the Planck's constant. So this wavelength, this is the de Broglie wavelength. Okay. So what he was saying was that electrons have wave-like properties and can be made to exhibit wave properties such as diffraction. Okay, de Broglie suggested that all particles travel through space as waves. Anything with mass that is moving has wave-like properties. Okay, so when he talked about particles, he was using electrons as an example, but he hypothesized that this was the same for other particles as well, such as protons and neutrons. So these waves, as I say, are referred to matter waves or de Broglie waves. So de Broglie claimed that all matter, regardless of its mass, could display wave-like properties. Okay. So it was already known up to this point that the wavelength of a light ray is given by Planck's constant divided by the momentum of the photon, okay, in the light ray. It may bother you to think that, hold on a minute, photons, how can they have momentum? Because momentum P is equal to m times v, okay, m being the mass. Now, photons don't have a mass. So if they don't have a mass and the mass is zero, then the momentum must be zero. Now that doesn't actually apply. It only applies if you're dealing with classical mechanics, and that would be correct. But this equation P is equal to mv doesn't hold, and it's not true when you're traveling near the speed of light. Okay, so this was already known. So you can ignore the fact that photons don't have a mass. You still get the relationship lambda is equal to hp. Okay, but we also know that P is equal to mv. We know at classical mechanics level that the momentum is equal to mv. Okay, and we also earlier derived this equation, lambda is equal to h over mv. So we can substitute P with mv, and this is for particles such as electrons. Okay, it could be protons, it could be neutrons as well. Okay, so the wavelength, the Broglie wavelength, is given by h over mv. It's also given by h over p because p is equal to mv. We would normally describe electrons as particles because why? Well, they have a mass and they have a charge. They can be accelerated and deflected by electric and magnetic fields. And we know that this behavior is only associated with particles. However, under certain conditions, we can make electrons diffract. They spread out like waves when passing through a tiny gap, forming diffraction patterns just like light. So basically, de Broglie's hypothesis, or what he postulated, actually was proven to be true 3 years after 1924, when an experiment was conducted and the wave property of electrons was confirmed. It was shown that electrons were indeed diffracted by single crystals of nickel. Now, this experiment can be done or reproduced in a school lab. We don't have this at Carshalton High School for Girls, but it can be done in a school lab. It is something that's shown in, for A-level students. Unfortunately, we don't have it. We can reproduce the diffraction results showing that electrons do indeed behave like waves as well as particles. Now, these two diagrams show that experiment that can be done in the lab. They're basically diagrams of the same setup, but one of the diagrams has slightly more detail than the other, so I've included it in to help you to understand what's actually happening in the experiment. So, electrons are basically emitted from a heated filament, which is also a heater or a hot wire. This is the source of the electrons, and this is also the cathode. And these electrons are accelerated to extremely high speeds by a large potential difference of up to 5 kilovolts or 5,000 volts between the negative heater or filament or cathode and the positive electrode called the anode that attracts the electrons. By changing the voltage between the cathode and anode, you can change the energy or kinetic energy of the electrons and therefore their speed as well. So a beam of electrons basically passes through a thin sample of polycrystalline graphite. Now, polycrystalline just means it is made up of many tiny crystals, each of which consists of large numbers of carbon atoms arranged in uniform atomic layers. Now, the electrons emerge from the graphite foil and, lo and behold, produce diffraction rings on the fluorescent screen. Okay, now this glass tube here, circular tube, just to let you know that that is vacuum. Okay, now the rings are similar to those on the fluorescent screen made by light wave passing through a small circular hole. And now we know that diffraction is a property of waves, so these electrons that are passing through the graphite foil are also showing wave-like properties. The electrons are diffracted by the carbon atoms and the spacing between the layers of the carbon atoms. So electrons pass between individual carbon atoms in the graphite. The gap or the spacing between atoms is so small, we're talking about 10 to the power minus 10 meters, that it is similar to the wavelength of the electrons, so they diffract as waves. In other words, the electrons diffract and overlap, forming an interference pattern on the fluorescent screen. The atomic layers of carbon behave like a diffraction grating, essentially, with many, many slits. Now, the wave nature of electrons is not something that we can easily notice, simply because we need a really, really tiny gap to get electrons to be diffracting, because as we know, the gap or the hole or the spacing must be equivalent in size to the wavelength of electrons to get any kind of diffraction. Okay. Now, here I've just made a sketch of the setup of the electron diffraction tube that we use here in a lab, with the power supply included as well. This is quite a unique power supply. So let's just talk it through. You have your evacuated bulb, which is obviously the vacuum at one end with the fluorescent screen there. Now, at the other end, we have what's called the electron gun, which is just the heated filament. And the heated filament releases electrons that are attracted to the anode, where they pass through a small hole. Now, why do we have this small hole? We have this small hole because it creates a narrow beam, which then travels across the tube and ultimately strikes the fluorescent screen. Now, we can see highlighted in pink over there this thin sheet of graphite foil, okay, which is placed in the path of the electrons. Now, it's this foil which causes the electrons to be diffracted. In order to use the electron diffraction tube, we need an extra high voltage power supply, which I've drawn in some detail there, which is called an EHT. EHT stands for extra high tension voltage supply. Okay, so this supply connects basically two circuits, one for the high voltage supply for the anode and a low voltage supply for the cathode to give us the large potential difference. Now, it is safe. The reason it is safe, because we're obviously dealing with very, very high voltages. It's safe because there's a high value resistor in series with the high voltage supply, which is shown on the left hand side. This EHT supply unit, I've drawn a little blue dashed line just to show the high output, and there's a low output voltage on the right hand side. Okay, so there we have the resistor in series with the high voltage supply, just so that the maximum current that you can get out of it is not really big enough to do any harm. Now you can connect the 0 volts of the high voltage supply to the earth and the 0 of the low voltage supply to the same earth. Okay, then connect the output of the low voltage supply marked 0 volts and 6 volts into the cathode, okay, as shown there in the diagram. Then finally you connect the anode to the high voltage output labeled 6 kilovolts, shown there in red. Okay, so that's how you would set this all up. After that, you switch your power supply on, and the cathode or the filament starts to glow, and then we can once it glows, you can turn on the turn the dial, I should say, on the high voltage supply, bringing it up to, let's say, 3000 kilovolts. Okay, and you should see a green dot surrounded by fainter green circles around that green dot on the fluorescent screen. That's the diffraction pattern produced as the electrons fly through the graphite foil or sheet. Now, this is just another diagram that I've annotated of the electron diffraction tube. So I've circled the filament or the cathode there. You can see the little dots are representing the electrons that are accelerated towards the anode, then through the hole to make the beam narrow, then through the graphite crystal, diffraction pattern there, and then you get the image formed on the fluorescent screen. Okay, and you can adjust using the dial the potential difference of the high voltage part of the circuit. You can take it from 3 kilovolts to 5 kilovolts and see what happens to the size of the rings. Okay, now we can use this electron diffraction tube as well to investigate how the wavelength of electrons depends on their speed. So increasing the potential difference across the anode cathode makes the diffraction rings shrink. We'll look at that in a little bit more detail. The electrons have more kinetic energy as they are faster, and the shrinking pattern shows that their wavelengths have decreased. So you can find the wavelength lambda of the electron by measuring the angle at which they are diffracted. And then you have an equation, lambda is equal to 2d sine theta, to work out the wavelength once you know the angle. And d, well, d is just the spacing of the atomic layers of graphite. Okay, and you can find the speed of the electrons from the anode cathode, knowing the voltage as well, using this equation, a half mv squared, the kinetic energy is equal to the charge on an electron multiplied by the potential difference. Okay, now the slit spacing is very, very large for a diffraction grating. That's why we wouldn't be able to use a diffraction grating to observe diffraction of electrons. Okay, so the diffraction grating slit spacing is very large in comparison to the wavelength of the electrons. So what we use instead is the this very thin piece of graphite crystal, because the spacing between the atoms is very, very small, 10 to the power minus 10 meters, and that is much more aligned with the, or of similar spacing for the wavelength of electrons. Okay, they both have a very similar size, both the wavelength of the electrons and the spacing between atoms. Now, if we look closely at the results of our electron diffraction tube experiment, the phosphor screen, which is the fluorescent screen, gives a flash of light for each electron that hits it. Okay, these flashes basically build up to give our overall diffraction pattern. But hold on a minute. If we're seeing flashes at particular points on the screen, then are we not seeing individual electrons? In other words, are we not observing particles? Yes, so there we have it. Electrons behave as particles when they're accelerated by the high potential difference, and then they behave like waves when they are diffracted, and then they behave as particles again as they hit the screen with these discrete impacts. Yeah. Now the picture on the left shows an actual photograph of the diffraction rings that are produced, and we can see these bright fringes, then the dark fringes, or in this case it's not actually fringes but rings. Okay. Since the graphite atoms are not all lined up in the same direction as diffraction grating, this actually gives this circular pattern rather than the parallel lines we're used to seeing with the white light that passes through a diffraction grating, causing the light to diffract. The image created on the fluorescent screen is created when electrons striking the screen cause the light to be emitted. So the fluorescent screen is designed to light up when electrons strike it. Okay. Now, increasing the energy of the electrons can be done by turning up the voltage, as I say, for example, from 3 kilovolts to 5 kilovolts. So increasing what we call the accelerating voltage using the dial causes the rings to get closer together, because with the increasing energy, the electrons have a shorter wavelength, okay, and so are diffracted less by the graphite, as shown in the picture on the right over there. Now, some might say that the beam looks like light, but you can prove that it's a beam of electrons creating the diffraction pattern by bringing a magnet close to the beam, and what you will see is that the pattern on the fluorescent screen is deflected. Okay, that wouldn't happen if the pattern was produced by a beam of light. Okay, it would only happen if it's produced by a beam of electrons, because electrons will be deflected by a magnetic field. Okay. Now, we can relate an object's kinetic energy Ek to its wavelength by considering both the de Broglie equation and our general equation for kinetic energy. So the de Broglie equation is given as follows. The de Broglie wavelength is equal to Planck's constant divided by the mass multiplied by the velocity. We also know that the kinetic energy Ek is given by a half mv squared. So just looking at the kinetic energy equation, we can multiply both sides of the equation by 2, and we get 2Ek is equal to mv squared. We can then multiply both sides of the equation by m, and we get 2Ek m is equal to m squared v squared. Then we can take the square root on both sides, and we have 2Ek m square root is equal to mv. Substitute this expression into the de Broglie equation, and we have lambda is equal to h divided by the square root of 2Ekm. As h and m are both constants, we can see that the wavelength of a particle is inversely proportional to the square root of its kinetic energy. So there we have it. Okay. Now, according to de Broglie's equation, all moving objects have a wavelength. Now, that includes solid objects like tennis balls, human beings, particles, electrons, protons, neutrons. Now, the greater the mass of the particle or the object, the shorter the wavelength. So macroscopic objects like tennis balls or human beings have such tiny wavelengths that diffraction effects are negligible. So they can be considered to be particles for all practical purposes. For example, we don't diffract as human beings when walking through a door. Let's take a look at an example and see why. So let's imagine there's a mass of a person, 65 kilograms. They're running at a speed of 3 meters per second. The opening width that they have to pass through is 0.8 meters, or the spacing. You can imagine that to be the slit spacing. Okay. Now the wavelength of this person, according to de Broglie equation, is given by h divided by mv. So lambda, the wavelength, de Broglie wavelength for this particular person, human being, is given by 6.63 times 10 to the power minus 34 divided by 65 multiplied by 3, which gives us a wavelength of 3.4 times 10 to the power minus 36 meters. Okay, that is really, really staggeringly small. Okay, now we already know that the wavelength, size of the wavelength should be comparable to the slit spacing, okay, or the opening width. And clearly that is not the case, because the opening width is 0.8 meters and the wavelength for the human is 3.4 times 10 to the power minus 36. Okay, so wavelength is very, very small indeed compared to the size of the gap. So no diffraction effects can be observed. The wavelength for a person must be much smaller than any gap a person is likely to ever try to squeeze through. Okay, we're never going to be able to squeeze through a gap of 3.4 times 10 to the power minus 36 meters. So we're not going to be able to observe diffraction of another human being. We don't use the wave model to describe behavior of a person. Better results are obtained by regarding people as particles. Okay, but that does not mean to say that we do not have a wavelength. There's our de Broglie wavelength, approximately 3.4 times 10 to the power minus 36 meters. So we've clearly seen that electrons can be shown to behave like waves. The de Broglie equation can also be applied, as we've just tried, to all particles. Protons and neutrons actually have been shown to have wave-like properties. However, particles, as they become larger, their wave properties become harder to observe. The mass of individual protons, for example, is much bigger than electrons. So at the same speed, their momentum will be bigger, and so their wavelengths are much smaller, so it's much harder to observe. Now, electron diffraction can be used to determine things like atomic spacing. It is also useful when determining other information about the structure of matter. Now just remember, increased speed results in decreased wavelengths, so much smaller values of interatomic spacing can be measured. Nowadays, high-speed electrons can be used to determine the arrangement of atoms in crystalline structures or to measure the diameter of a nucleus. So very, very useful work there, thanks to de Broglie. So just a quick summary then. Wave-particle duality says that things that we normally think of as waves can behave as if they are particles, and things that we normally think of as particles, such as electrons, can behave as waves. So if we look at the light, we know that it can behave as a wave through the Young's double slit experiment, but we also know that it can behave as a particle thanks to the Einstein photoelectric effect experiment. Electrons, well, using electron diffraction tube, we can show it to have wave-like properties. But in that same experiment, using the electron diffraction tube, we can show electrons to behave like particles. For example, when they are accelerated from the cathode to the anode. Okay. So let's take a look at an example question that may come up that we need to practice. Let's see. Calculate the de Broglie wavelength for an electron traveling through space at a speed of 10 to the power 7 meters per second. State whether or not these electrons can be diffracted by solid materials. Solid material here has an atomic spacing of approximately 10 to the power minus 10 meters. Okay, so what do we do first? According to the de Broglie equation, we have the de Broglie wavelength is equal to h divided by m times v. The mass of an electron is 9.11 times 10 to the power minus 31 kilograms. Hence, we know Planck's constant, so we can work out the de Broglie wavelength. The de Broglie wavelength is given by the equation there, which if you plug in the numbers, we get 6.63 times 10 to the power minus 34 divided by 9.11 times 10 to the power minus 31 multiplied by 10 to the power 7. Okay, and that gives us a de Broglie wavelength of 7.3 times 10 to the power minus 11 meters. So from that we conclude that electrons traveling at 10 to the power 7 meters per second have a de Broglie wavelength of the order of magnitude 10 to the power minus 10 meters. Hence, they can be diffracted by matter. Okay. Okay, now it's your turn to have a go at a couple of questions here. Okay, I just want to give you another tip as well in terms of the thinking behind this when you're thinking about the de Broglie equation. Now, the only way to get a meaningful wavelength is really with a very light particle. In other words, a particle that doesn't have a very big mass. Okay, and also we don't want it to be traveling very, very fast. Okay, otherwise what happens is if you have something that has a very large mass and is traveling really, really fast, the wavelength will be too small to get a diffraction pattern. Okay, so it's got to be of a reasonable speed because it's got to be fast enough to get through the, let's say, graphite foil. Okay, but we don't want it to be extremely fast, otherwise the wavelength will just be too small to get any sort of diffraction pattern. Okay, so have a go at these questions, pause the video and see how you get on. So here are the answers to those two questions. How did you get on? I hope you were okay with it, didn't struggle too much, and look forward to delivering another session via these YouTube videos very soon. Have a great day.